Okay, so we've got a lot of noise outside today, but reasonably quiet when the door is closed, I guess. We can actually talk about this phenomenon a little bit today because the fact that it's a bit quieter in here is mostly due to the fact that we have a multi-medium uh, boundary between the outside and the inside. So, for example, in this area where there are doors, there's this little airlock where there's air, a wooden door, air, a wooden door, air. And those types of multi-medium boundaries tend to cause lots of reflection to occur, which is good for us because it's reflecting all of that sound back outside. And it's a really nice phenomenon to be aware of if you're trying to like soundproof your room or something. People tend to just want to grab a bunch of foam, which is an okay solution, but it's much more efficient to try to create layers of rigid material and then some air gap and then another rigid material. But anyways, so we're in chapter 17, thinking about superposition and standing waves. And the last thing we left off on was this idea of boundary conditions as they apply to string waves. And the way that we solve these things mathematically, the initial conditions we saw in chapter 15 and the boundary conditions we see here in chapter 17, they're kind of similar ideas, similar types of information, in that we're going to have structures, mathematical structures that we're using to describe the waves, and we use information about the boundary to kind of pick which system type we're experiencing. And so the distinction, and really the only distinction that we'll see in this class, is between a fixed end, where notably there's no displacement, so d is 0 at that point, versus a free end where there will be an antinode, so there will be a maximal displacement at some times that will alternate as the system oscillates. And so just like I was saying, when we have a wave traveling from one material to another material, the experience is similar to one of these boundary condition situations. So you can see for a fixed boundary, we get a reflection that's reversed. And for a free boundary, we get a reflection that looks the same as what came in. And so on the left, we see that when we go from a more massive string to a less massive string, that this is similar to a free end. And the reason is that the more massive string has more inertia, so it can more easily move the less massive string. So this boundary where we go from one type to the other is able to move up and down as this energy passes through. So it acts like a free end. However, when we go from a less massive string to a more massive string, the less massive string, which is what the wave pulse is traveling on, has less inertia than its more massive counterpart. And so when this wave comes through, it actually doesn't move that boundary very much. And so that acts more like a fixed end. I kind of crappily labeled these on the bottom. And so for that less massive to more massive case, we get an inverted reflection. And then on the right is the sort of classical fixed case, which is where we have a rope tied to like, a desk or a wall or something. And so that's just very clearly a fixed boundary because it's attached to some rigid structure that just can't move. But the cases where we have changes in linear density, these are a little bit trickier. So make sure that you think through how the left picture acts like a free end and the middle picture acts like a fixed end. And so when we have some situation like in this room where there are sound waves outside that are traveling in air, which is a medium with a very low density, and then they travel through a wooden door, which is a medium with a very high density, that's really similar to this middle picture. So that'll act like a fixed boundary. And then as those waves that are inside the door travel into the next pocket of air, that acts like a free boundary, so like the image on the left. And if we make waves do this over and over again, they'll tend to reflect a lot of their energy away, which we are experiencing right now. So are there any questions about this slide before we keep going? Okay, and I got a really good question, actually. I'm gonna go, don't worry that I'm going back so far, but I'm gonna go back slightly just to the chapter or the section on superposition. So I got a really good question, which is, Canon, energy is conserved. Waves have energy, right? They're distended harmonic oscillators all connected together. So they have some sort of 1/2 kx squared type of energy to them. So how is it that superposition can be destructive, right? Am I not destroying energy when I do that? Or alternatively, how can superposition not be, if it's constructive, how is that working? Am I not creating energy? And so the way that I would answer this is to say that superposition is a temporary local phenomenon. So it's, what I mean by temporary is that as the waves pass through each other, once they're all the way passed through, they're going to look the same as before they started. So that obviously has some sort of energy conservation if you look at before the collision happens and after the collision happens. But then you might say, okay, well, what about during that process? And so it is true that, for example, the waves in this region, as they destructively interfere, are reducing the energy in that region. If your ear were there, no matter how loud the constituent waves were, you wouldn't hear anything and it wouldn't be damaging to your ears. So noise canceling headphones do in fact locally, so in the region where they're destructively interfering, they do in fact take away that energy from the wave. But in general, the wave is spatially, larger than the region where there's interference. So if we think about some sine wave here and some sine wave here, they're traveling into each other. There will be little bits of time where they destructively interfere, but other bits where they constructively interfere. And so the net effect over longer space and time periods is that energy is conserved. And we can actually go into more detail and say that it's even conserved during these moments of superposition. That's a little bit harder to show, and especially in the cases of these wave pulses, which are in some ways an approximation, less obvious from the pictures. But mathematically, energy continues to be conserved even during the process of superposition. But if that feels weird to you, just think about superposition as a very temporary state of the world, and that after the fact, it'll go back to waves that are similar to what you started with. Okay, so then we're now ready to talk about how we can get the form of standing waves on a string. So if we have a string, well, I'll just draw it for us. If we have a string that's fixed on both ends, so one is at a position 0 and one is at a position L, and we call this the x-axis, and then this is our displacement d. So these are our ends. So how can we figure out what the standing waves on a string like this, where both ends are stuck, what these standing waves look like? So we already used, so just to write down the formula d of x comma t, we had this a of x times cosine of omega t, and our a of x was this 2a sine k kx. Okay, so this is our equation for standing waves, and to get this, it's derived in the book, but remember, all that we did was we took one wave traveling to the left, one wave traveling to the right, but they were otherwise the same. They had the same amplitude, the same frequency, and we asked mathematically what happens if we use trig identities to add up these two sinusoids, and we are able to get this separable solution where all of the x variables are in one trig function and all of the time variables are in another trig function. And so remember, this cosine omega t term, that tells you how the wave is changing over time. And the 2a sine kx term tells you how the wave looks spatially. So if you took a picture of it, a snapshot, what would that wave look like? And so if we want to figure out what these standing waves look like based on the boundary conditions I described to you, where we fix the left end and we fix the right end, what we have to do is first we say that, okay, 2a sine kx, that this has to equal, so if x is 0, that this has to equal 0, right? There's no displacement, 0 displacement at the position where x is 0, because that is a fixed end. So we apply the boundary condition. Sorry, I'm gonna write that again. But this is quite boring, because no matter what k is, sine of 0 is just going to be 0. So this doesn't really tell us anything interesting. So this is sort of not interesting. But what is interesting is if we apply the same condition to the boundary at x equals L. And so that's what we do here. So we say we plug in L, the length of the string, for x. And the reason we do that is because at position L, we have a fixed end of the string, a fixed boundary. And so then we solve. The 2a goes away, and we find that so sine of KL has to equal 0. So KL has to be at one of the angles where sine is 0. So that happens here, that happens here, that happens here. Every multiple of pi over 2. And then we can rearrange a little bit. So we know that k, the wave number, is defined as 2 pi over lambda. That was what we took to simplify our traveling waves in the last chapter. And so we can replace this k with 2 pi over lambda times L equals m pi over 2. Our pi's go away, and did I do something a little questionable here? Sorry. These shouldn't be multiples of pi over 2. I'm getting ahead of myself. That's going to be the next boundary condition. So sorry. Sine is at 0, it's 0. At pi, it's 0. At 2 pi, it's 0. So these should be multiples of pi. Apologies. And so rearranging, we get that lambda is 2L over m, the lambda of m. And that's this condition here. So for a string that's fixed on both ends, this is a really fundamental phenomenon, and it's actually very similar to what you see in quantum mechanics, and that's not an accident. Quantum mechanics is in many ways the study of treating matter and probability as waves. But what we see is that there are only certain values of the wavelength that will actually work, that will actually make a standing wave. So what that means is that if you have a guitar string, which is a great example with similar boundary conditions where it's fixed on one end and fixed on the other, so the two ends can't move, and we pluck the guitar string, only certain types of plucking will actually make a standing wave. So you can, if you pluck a guitar string, end up making some weird wibbly wobbly thing that doesn't actually look like a standing wave. It looks like it's maybe traveling a little bit back and forth. But if you pluck it at one of these sort of natural frequencies, which for reasons that we'll see later, even if you do a combination of these natural frequencies and others, the natural ones will kind of dominate and you'll mostly see their behavior. So that can be a little confusing. But basically only certain frequencies will actually cause standing waves to form on a string like this. And if we convert wavelength to frequency using the velocity, we can find the frequencies of these standing waves. And we call these harmonics. So when m equals 1, this is often known as the fundamental frequency. And you can see m here for frequency is in the numerator. So m equals 1 is the lowest pitch that you can make with a system like this. Okay. So when you actually, when you are singing in the shower and you sing the lowest note you can, that is roughly matching the fundamental frequency of your vocal system. Of course, our vocal system has different boundary conditions. It's not fixed on both ends. So we'll talk about how to actually find that frequency soon. But you can kind of get the idea of what a fundamental frequency is. It's the lowest note achievable by a given system when you're thinking about that in the context of standing waves. And this is also called the first harmonic. which is terminology that may be familiar to you if you have a lot of music theory education, but we're not going to get into those details because that's a whole long tangent here. So when m equals 2, this is called just the second harmonic. It doesn't get its own fancy name. And you can probably guess what higher m's are called, just the mth harmonic. Okay, so then you might ask, what do these look like? And we're now finally ready to come back to this slide. And I just dropped a bunch of text on here if you want to come back to these slides later. This is just from the book, but I think these are important observations about what standing waves look like. But I'm going to try to just describe them to you in words so you don't have to read that giant block if you don't want to. Let me move this over here. But you can see here we have a string of length L. Some people get confused because, when the string is stretched, it's longer than L. But we ignore that when we're talking about waves on a string. So we can always assume that any displacement is reasonably small compared to the length of the string when we're doing this type of analysis. And even if it's not true, that gives a pretty good approximation. So you can see that when we have this first harmonic or this fundamental mode, we have a formula for the wavelength. It's just 2L over 1. And so you can see that's what we have right here, 2L over 1. And the frequency is just 1 times V over 2L, which is what they write here. So this F1 is the fundamental frequency of this system. And you can see that lambda 1 is 2L. So what that means is that if we wanted a whole wavelength, we would have to keep going, right? This is half a wavelength along the string. And so if we wanted a full wavelength, we would have to keep going one more string length to the side. And so the fundamental mode for this fixed boundary condition is only one hump, basically. And that you can see that it's going to oscillate up and down. So this is what we usually think of, I think, most intuitively when we think of a standing wave. It's just one, you have a string, you pluck it, and it's not looking like it travels to the sides, it just oscillates up and down. That's a standing wave. And that's this fundamental standing wave for a fixed system. But you can say, what happens when m equals 2? So you can see in all of these pictures, we have 0 displacement on either end. So that's why these are valid solutions to the standing wave equations based on the boundary conditions we have. So for m equals 2, the second harmonic, we have something where there's a whole wavelength. So, you can think of it like a sine wave, a chunk of a sine wave, and then it's going to kind of wobble back and forth like this, right? So this picture would be what it looks like at one time, and then it's going to go flat, and then it's going to look like this at a later time. That's kind of the picture. And then we get more and more crazy. But, all of these are just chunks of a sine wave, basically. So you can see for m equals 3, we just have 3 halves of a wavelength. For m equals 4, we have 2 wavelengths of a sine wave. And so the observations on the side, we've covered a few of them already just by talking. One more of them, though, is that the number of nodes in a system will be m-1. So the number of nodes for these fixed systems will be m-1. I don't really remember these facts myself. I'll just draw the pictures like this and try to remember them that way. So that's what I would encourage you to do, unless you just really want to remember a bunch of formulas, in which case, feel free. I'm never going to complain about that. And then the number of antinodes actually just equals m. So the number of antinodes is just m. And these facts are specific to the fixed boundary conditions. Right, because if we have different boundary conditions, we'll have different types of sinusoid, you can imagine. Okay, so this is probably the most important slide of this set of slides. This is really getting at the fundamental idea of what a standing wave is, what they look like, and then how do we calculate their wavelength, their frequency, and understanding the important idea that there are only certain frequencies for a given system where you actually get a standing wave. That's, I think, really something that takes some time to get used to. Because when you think about talking, you can kind of make whatever frequency you'd like within a certain range. So we don't really think about these quantized frequencies in our normal speech or in everyday life, but for most systems, they're much more constrained. And in fact, the only reason that humans can make so many different types of sounds is that we're constantly changing the length L, so that's one of the factors in this, and we're changing the boundary conditions of our vocal tract, right? So when you make the letter P, you're temporarily making a fixed boundary condition. You have the air fixed in your chest and the air fixed at your lips when you make the sound P. But when you make like an ah sound, you have a fixed free boundary condition. And if you make an E sound instead, you have another fixed free boundary condition, but you've shifted the length of that track, right? Now it's back where your tongue is when you say E, compared to ah, where it's the entire length out to your lips. So the human vocal tract, really amazing. It's a whole bunch of types of systems all mixed into one. We can really control it to a high degree, and so we can achieve lots of frequencies, even though an individual fixed type of system would only be able to achieve these set number of frequencies. And then the other thing I want you to notice is that the frequency here, it's 1 V over 2L. Here it's 2, 3, 4. So a very useful tip that you will certainly use in the homework and maybe on the quiz is that if you know 2 ordered harmonics, so if you know the m+1th harmonic and you know the mth harmonic, if you just subtract these, you will get the fundamental frequency. So that sounds like, when you first see this, it sounds like some weird craziness, but all that's saying is that, look at the formula. You're going from 1 V over 2L to 2 V over 2L to 3 V over 4L, 4 V over 4L. So each time you're increasing by V over 2L, which is exactly what F1 is. So if I tell you 2 ordered, if I tell you the 1,000,002nd harmonic and the 1,000,003rd harmonic, you can just say, okay, I'll subtract those 2 frequencies. Maybe one is, I don't know, a kilohertz and one is 1.2 kilohertz. I subtract those 2 and I find the fundamental frequency immediately is just 200 hertz in that case. Okay, so we'll get some practice with that, but it's a very nice trick, very handy to see that these are just 1, 2, 3, 4, 5. It's just, the numbers. Okay, so any questions about this slide? Really important slide. Okay, good. So let's do a little bit of practice here. So a standing wave on a string vibrates as shown at the right. Suppose the string tension is quadrupled while the frequency and the length of the string are held constant. Which standing wave pattern is produced? Okay, so when we quadruple the string tension, what are we changing? How does the string tension play into the variables relevant for wave formation? Exactly, velocity. So our velocity formula was root T over mu. So if we quadruple the tension, what happens to the velocity? It gets doubled, exactly. Okay, so we have twice as much velocity. Now let's think about what they're saying. They're saying the frequency and the length are constant. Okay, so if we go back to this formula, the frequency is constant and the length is constant, but we're changing this velocity. Okay, so what's going to change? Well, there's only one thing left to change, which is the harmonic that we have that's oscillating. Okay, so if we double the velocity, then you can see we have to have the harmonic. So we are currently at a harmonic m equals 2 here. So if we've doubled the velocity, we have to have the harmonic. So we're over here at m equals 1. Okay, so the way that you would cause this to actually happen, let's talk about how you would cause this to happen. So to make standing waves, right, you can just vibrate in the middle. So what this is saying is that you start vibrating in the middle of a guitar string, and like you're strumming the string, maybe is one way of thinking about it. and you keep strumming at the same rate. So that's how you keep the frequency the same. But as you do that, you start tensioning it, right? And guitars actually do this. When you tune a guitar, that's just increasing or decreasing the tension. So what this problem is asking is if you are plucking the string on a guitar and you see the second harmonic, and you tune it all the way to the point where you've quadrupled the tension, which is actually unrealistic for guitars, but you can imagine, then what would happen is that second harmonic would turn into the first harmonic, or the fundamental frequency. So there's this really nice connection. You can think about how you would physically do this. I personally love just thinking about guitars, even if you try to go beyond the boundaries of what is realistic with them, they're a great system to get some intuition with. Okay, so questions on this one? So, maybe it's helpful if I write the formula on this page as well. So Fm is m times v over 2L. So we're holding this constant and we're holding this constant. So the only two things that can change are v and m. So we replace v with 2v, we have to replace m with m over 2. That's the idea, so that the 2's cancel. Okay. So now we move on to section 17.4, where we can talk about standing waves in the form of sound. So I've already been alluding to them. Mathematically, of course, they're going to be very similar, but it's good to talk about sound waves specifically. And I actually pulled these two pictures. They're not from the book, but this is from one of my favorite places. So there's a Philharmonic, the Elba Philharmonic in Hamburg, which is this beautiful building right on the harbor. And they have one of the grandest organs in the world. And the pipes in this organ range all the way from the size of a few millimeters up to the size of many meters. So it's a dramatic range of pipe size. And the reason for this is that it allows for a dramatic range of notes that can be played. And by having separate pipes, you can play these notes simultaneously, which is really convenient. And so I went to an organ show there, and they have actually the control system right in the middle, and then it sends the signals through the ground to actuators that can push air to create the standing waves in each of these pipes and play some beautiful organ music. So it's a really magical place. It also has great acoustic properties that are probably beyond the scope of this course, but nonetheless interesting. So, okay, if we have a standing wave in a pipe, and we can start by thinking about a closed pipe. So for example, when you're, if you close your lips and hum, that would be a standing wave in a closed pipe that you can maintain for some length of time. So in that case, we can look at these bottom images to see what the actual air molecules are doing. And what you can see is that the air molecules on the boundaries go from very low density on the left to uniform density in the middle to very high density on the right. Okay, and so we can model that density as a sinusoid, and it turns out that that's accurate to very high precision. And so this closed pipe system, if we think about how much the molecules are moving, so the side-to-side displacement of the molecules, or similarly the density of the molecules, then we get these graphs that are shown here. Now, we can also think about the pressure in a system like this. And so if you think about the pressure, I don't know if your book gets into this, but just to draw this for you. If this is 0 and this is x equals L. So you can see that the pressure, it's still one wave, one sinusoidal wavelength. So this is still lambda, and this is lambda. So everything's the same, but it's shifted. So when we think about the pressure graph for a sound-based standing wave, it will be a pi over 2 shifted version of the displacement graph. And so this is really confusing sometimes because you'll be trying to think about the intuition. You'll be like, imagine yourself in a pipe and you're like, how are the air molecules moving? And it's very easy to accidentally mistake pressure for displacement. I personally like thinking in terms of pressure because you know that for an open tube, the pressure has to be atmospheric pressure, which we can take as zero if we're thinking in terms of a pressure gauge. And so for a closed system, the pressure will be highest on the boundaries. And so it'll oscillate between something that looks like this and something that looks like this. And so you can see for pressure, these are free ends. So what we call a closed pipe, for if we think of in terms of pressure, they're free boundaries on either side. But in terms of displacement, they're fixed boundaries on either side. But the magical thing that you can see from the fact that I called both of these length lambda is that the wavelength and the frequency are the same, right? Obviously, these are both describing the same system, so they have to produce the same sound that we hear. And so a really important fact that you can see from this slide is that if we have free boundary conditions, which is what we see in the pressure graph, that this is functionally equal to fixed boundary conditions. So as long as both sides are the same, we'll end up getting some integer number of wavelengths, or the fundamental half integer, I guess, in the string, and end up with the same numbers for the frequencies of the harmonics. Okay, so this is a really great thing, actually. It simplifies our analysis a lot. So this means that we only have two types of standing wave systems. We have ones where the boundaries are the same on both ends, and ones where the boundaries are different on each end. So everything we've learned so far about fixed standing waves, so like all this slide stuff, is also going to be true for the free ends. Okay. Excellent. And so you can see, okay, I think we've basically exhausted what's interesting on this slide, but basically when we have a tube, we can create standing waves in terms of sound. And even if some systems isn't a tube, like in this room, we can think of from the back wall to, or the front wall to the back wall as one tube. We can think of the side to side as another tube, and we can think of up and down as another tube. So in a way, a box is like 3 tubes in a trench coat. But if you have more complex shapes, then there will be lots of tubes that you can think of. And so that's why, in some instruments, we get really tricky geometries that are able to produce really unique sounds. This is an important part of, and I guess the best example of that, again, is the human vocal tract. Okay, so let's actually do an example though, because it's been a while since we did one. So we have a shower stall that's 2.45 meters tall, 8 feet tall, which is like a standard household wall height. For what frequencies less than 500 hertz are there standing sound waves in the shower stall? Okay, so this is a shower stall. So in terms of displacement, this is a fixed boundary condition. But like I said, in terms of pressure, this would be a free. So we could, either way, we'll get the same answer. So it's just a personal choice. And so we can think of this in terms of, the standing waves we've seen so far. So we've got one like this. We're going to have one like this, right? We're going to have one like that, just to give you some examples of what these different harmonics will look like. But the way the question's phrased, we have to really think carefully about what we should do here. So we know that our equation for the frequencies, Fm, is m times v over 2L. And the nice thing about sound waves is that to a good approximation, you immediately know the velocity. It's just the speed of sound, 343 meters per second. Okay. And they tell us what L is here. So the height of the shower stall is 2.45 meters. So since that's probably the longest dimension in the shower, that'll allow us to get the lowest notes, right? The bigger L is, the smaller the smallest frequency will be, the fundamental frequency will be. And so the lower the note achievable, right? That's why if you want to play a very low note on an instrument, you need a very large instrument. That's why we have basses and cellos and tubas. These are all instruments that use their length to be able to achieve these low frequency standing waves, which we can see from the equation immediately why that's necessary. Unless you want to start messing with the speed of sound, which is, I guess, another option if you want to play underwater or something. But anyways, so we can then use this 500 hertz to find what harmonic that is. Okay, so we have 500 hertz, and we know that that's some harmonic, and we want to solve for which. So we say m times 343 over 2 times 2.45. And so we get some value for m, and m has to be an integer. So oftentimes you'll like find a value for m and it won't exactly be an integer because of calculator error, or maybe something about the approximations you're making in that problem. Sorry. They're not telling you that 500 hertz is a fundamental frequency. I misread this problem. Sorry. If they had said that this is some FM, then we could solve it this way. But they just ask what are the ones that are less than this. So I guess we're just stuck first finding F1, which would just be V over 2L, which I have in my notes here, is 70 hertz. And then just listing all of the ones above that. So they're going to be spaced apart by F1. So F2, we don't even need to calculate. It's just going to be 140 hertz. F3 is 210 hertz. F4 is 280. F5 is 350. F6 is 420. And F7 is 490. So we have, okay, sorry about misreading that problem at first, but we have 7 harmonics that are below 500 hertz in this system. So 500 hertz itself is not one of the harmonics. They're just asking you to list all of them. And so I guess we could have just solved for what m is for 500 hertz and then just said all of the m's below that. So that, I guess I shouldn't have immediately discounted that option. So if we just said this, or we just made this a greater than sign, then we would solve this and we would get m less than, 7 point something. So we could just say m less than, I don't know, 7.2 or something. So we would say that for m equals 7 and below, we have valid harmonics under this constraint. Okay. So any questions about how to solve this one? Good. Okay, so here's the slide I brought in to talk about comparing pressure and displacement. If this slide looks terribly confusing, you can just have the takeaway that it doesn't matter whether you use pressure or displacement, you'll get the same answers. They have different boundary conditions. One of them will be, free, for example, in some situation. Another will be fixed, but those two are equivalent for that type of system. Okay, so we see on the left, we have a completely closed tube. So this is like the shower, where we have a wall, a floor, and a ceiling, closed tube. And so you can see that we get a pressure antinode at the one side of the tube and a pressure antinode at the other side of the tube. But we get a displacement antinode in the middle. So these are all of the antinode locations for the fundamental harmonic. And then they also show the m equals 2 harmonic. So you can see in pressure, we still have these antinodes here, and here. So one on each end. And for displacement, we have our antinodes here and here. So for displacement, for a closed system, there are nodes on either end. It's 0 displacement. And for the pressure, there are antinodes on either end. So maximal pressure. It won't always be maximal, right? It's fluctuating up and down, but that's where we achieve the biggest values when they occur. Okay, so for an open, you can see how it's exactly the same graphs, but they're just flipped, right? What used to be the pressure graph is now the displacement and vice versa. So a closed, and an open will actually achieve the same frequencies. So if you're designing, just to make this practical, if you're designing a musical instrument, you can have a closed box of gas, or you can have a completely open tube. And both of those, if you vibrate the air inside, will produce the same spectrum of frequencies. So if your fundamental frequency in one is 100 hertz, it'll be 100 hertz in the other. And, as long as they're the same length and have the same fluid inside, in this case, air. But the open closed one, so this one is different. So this is our first time seeing what a mixed boundary condition looks like. And so I think it's worth getting into the details of. You can see here for the displacement that what happens is we have no displacement on the closed end. So on the closed end, we have no displacement, but on the open end, we have an antinode. And so what this graph looks like is it looks like 1/4 of a wavelength. Right, it's half of a hump. So that's the fundamental frequency. And then the next mode, we actually skip. So there's no m equals 2. M equals 2 doesn't exist. And the reason for that is that we can't, so think about what we're doing. We want a fixed end on one side and a free end on the other. So we can do that with 1/4 of a wavelength. And so then you might say, well, what if we just go up by another 1/4? That would be a half a wavelength, but that would just be one hump. So that wouldn't satisfy the boundary condition. So we have to add not one extra 1/4, but another. So this is our m equals 1. And then our next mode that actually exists is m equals 3, where we start again at 0, we go up, down, and then we have an antinode at L. So for the mixed boundary condition case, we only have odd harmonics. This is a really important idea. So if I ask you, if I say, think about a tuba or something where you blow in one side and it's open to the air on the other. So this would be a mixed boundary condition situation. And I asked you, what's the 1/1,000,000th harmonic of a tuba? You could just say, no thanks, Canon, that doesn't exist. If I asked you for the 1,000,001st harmonic, then you have to start plugging into an equation. And so these waves, they, again, whether we choose pressure or displacement, it doesn't matter. We should get the same answers for frequency and wavelength, but it does change what our graphs look like. So you might be asked to identify the correct displacement graph for some boundary conditions or the correct pressure graph. Just remember that, here's how I would remember it. Pressure that's open to the atmosphere has to be 1 atmosphere. We call that 0. So any open end, the pressure will be 0. I think that's the easiest part of all these things to remember for the sound boundary conditions. If it's open, pressure is 0. And so on the closed end, the pressure will be an antinode. And displacement's just going to be the flip of that. So for displacement, you'll get an antinode, so the most displacement on an open side, and the least displacement on a closed side, because the molecules can't move through the rigid object. So that's how all these graphs come about, basically, is just thinking about which possible chunks of a sinusoid could satisfy the boundary conditions we impose on it based on how we make our object, whether it's solid object or open or a mix. Okay, any questions about these 3 possibilities? Okay, and we can talk about all of these have an analog in terms of strings, right? So if we have a string like a guitar string that's fixed on both ends, that would be our closed system. If we have one that is has a ring tied to each end and then that's slipped around a stick, so the whole thing can move up and down, and we start wiggling that would be like the open. And if we have one side of a string stuck in place and the other side with a little ring that can move up and down, that would be like the mixed boundary condition. Okay, So I'm going to summarize everything here in terms of the frequencies and wavelengths. So if we have the same boundary conditions on both ends, then we use these formulas, and these are the ones we've been using so far, the ones we used in the shower example, where we have lambda is 2L over M, and the frequency is mv over 2L, and they also give you the helpful formula that the mth harmonic is just m times the first harmonic. Okay. However, if the two sides are different types of boundaries, then we have these formulas. So you can see here, importantly, m can only be odd. We only have odd modes for the mixed boundary condition case. And we have not a 2, but a 4 here in the equation. And that's because we're thinking in terms of quarters of the wavelength, right? So in this situation, the first harmonic is 1/4, the second harmonic is 3/4, the next harmonic is, I'm going to struggle to draw it here, like this, 5/4. So this side is at 0. And this side is an antinode. So those are what the harmonics look like for this mixed boundary condition case. And that's where this factor of 4 is coming from. We're thinking in terms of chunks of the wave that are broken up into quarters. And the reason for the odd multiples is because we can only have things where we have an odd number of quarters in order to have a 0 on one side and an antinode on the other side. Okay, so this is a good reference slide to come back to as you're doing the homework, just because it'll be, the vast majority of the case, the set of equations that you're interested in. Okay, so let's try this example. So we have an open tube of air that supports standing waves at frequencies of 300 and 400 hertz. Okay, so here the frequencies they give us are actually standing waves in the system. And at no frequencies between these two, the second harmonic of this tube has what frequency? Okay, so this is an example where we want to use this trick, right? That if we know the m plus 1th frequency and we know the mth frequency, we can subtract them and we'll get the first harmonic. Okay, and this is an open system, so we can just do that directly and don't have to think very hard about it. For a mixed system, I encourage you to practice on your own to figure out what this equation looks like under that condition. Since we don't have the even harmonics, it's a little trickier. Okay, so in this case, we have 300 and 400, and they say there are none in between. So we can immediately say that the fundamental frequency is 100 hertz. And then the second frequency is just going to be twice that. So 200 hertz. We get option B. So this is a problem that it's very easy to take a ton of time solving this problem, right? It's very easy to say, okay, 300 and 400 hertz, and then you try to solve for the speed of, or you try to solve for the length of the tube, and you're like, I know the speed of sound, and then you're like, I don't know m, and it just gets really messy, and you write a whole page of stuff, and then eventually maybe you get the answer, maybe you don't. So it's one of those cases. Physics sometimes is the land of trickery. So you've just got to get used to using tricks like this. So thinking in terms of an arbitrary harmonic. And since they tell you a relationship between two arbitrary harmonics that are separated by, 1m, we want to try to develop some mathematical relationship that describes that sort of situation. And so we can just memorize this one as an example, but in your future, you'll encounter, maybe in this class, maybe somewhere else, problems of this sort where you are given some piece of information that doesn't quite match what you already know, what formulas you have. And so I would encourage you to stay in the realm of variables. Don't just immediately plug in, and try to come up with what sort of relationship would be valid in that type of situation. And this is all very abstract, but hopefully you can see this example here where we say in general, sequential harmonics are, the difference is just the fundamental frequency. Okay, so we're about halfway through, so I'll pause here and give you 5 minutes to take it all in, and then we'll start talking about the magic of Fourier transforms, but just abstractly.
I had a question about my project. I think it was ultrasound, and the question like why did it choose a certain intensity? I can hear you, but and I think you told me that like finding negative intensity pain threshold.
Mhm,
The only one that mine is regarding years,
mhm.
but I don't think it's really good. Like
No, that's a good point. That's a good point. So I would say the way that, um, like the way that decibels are a logarithmic scale means that by the time you're at a pain threshold for the ear, even though you're totally right, it's going to be different for the body and thinking about when our cells going to rupture and things like that. But you know, the types of intensity that are able to move the eardrum, for example, to such an extent that they can cause physical pain, are also going to be able to move other small bodily structures at a similar scale, such that they could potentially cause problems. So it's not a perfect metric, and I'm glad you talked to me about it, but I would say for the level of approximation, you know, that's reasonable for these projects, that you can take that type of approximation.
also I saw a paper when I was looking up the intensity for ultrasound, taking like the range for imaging is 0.005 watts per centimeter squared to 0.5. And then the next slide said, oh, the range is definitely 0.003 to 50,000 or something. And so I looked in there and then they had a chart. And the range is what like 0.05 to 0.5 was of the imaging. And right below it, that larger showed like the exaggeration and all that. That would kind of cause damage.
Damage.
So the range the pain was bigger than the one for imaging. So I don't know.
I would, yeah, no, that's very reasonable. So I would say for imaging, just think about those lower ones, because like you said, the higher ones are really saying you're destroying something.
Yeah.
And the way that works is that if they do something like looking at standing waves and they just have the high amplitude be where the cancer is. So it's a very localized, you can actually make this really localized where it only is destroying cells in a tumor or something.
Okay.
So yeah, you could actually even take those intensities as the dangerous intensities, because if you're not carefully applying them and doing it very locally to a cancer tissue, you would destroy human tissue.
That's the issue, like the dangers, like the intense range that they gave that could be used for surgery.
Mhm.
Larger than the
So-
range for the imaging was.
I'll look into this. Have you sent me an email about this yet?
No, I-
Okay, so send me one. And what's probably happening is they're doing something like this, like we've been talking about with standing waves, where you have superposition. And so you, even though you have some set intensity, by carefully manipulating the wavefronts, you can actually make it constructively interfere only where the cancer is or something. So you can effectively double you know, the energy.
I think email and then like the link to it.
Good. I'll look through the study for you.
Yeah, thank you.
Thanks, guys. Okay, so hopefully a good break. So we're jumping over to the next section, which is the physics of speech. And there are a lot of sort of qualitative things in this section, but not a lot of quantitative things. So hopefully it's a good thing. But there is a whole quantitative aspect of this. It's just kind of beyond the scope of this class. But I do expect you to understand from section 17.5, basically, what a frequency spectrum is. That's the important idea. Okay, so when you, in this example, play guitar, it's really not typically just one frequency that you're producing. So some instruments are very good at producing single frequency tones, but that tends to sound kind of weird to people, a little unnatural, which can sometimes be the effect you want. But oftentimes by, you know, just simply strumming a guitar string, you're actually activating a bunch of standing waves at once. Because when you strum a string, it's not a precise motion. So you can sometimes activate, the fundamental harmonic, maybe the second harmonic, maybe some higher ones as well. And so that's what this plot in figure in part A is showing, is that we have the frequencies on the x-axis and then the relative intensity on the y-axis. So you can see that there's a lot of energy at this 262 hertz peak. And so as the chart notes, that's likely the fundamental frequency of the string. So if I gave you one of these frequency spectra, and I said, this is for a string, a fixed string, like a guitar string, and you see one of these peaks is really, really high, that's some sort of harmonic. And if it's a low frequency, if it's the lowest frequency seen on the plot, then that would be the fundamental frequency. Okay, so that's one important thing to know here. I don't think it's, okay, the screen here keeps going dark. I'm not sure what's going on there, but hopefully the projector stays working. And then we see all of these other peaks as they label. These are higher harmonics, and you can see they're all spaced apart by the same amount. And the amount they're spaced apart by is, of course, going to be 262 hertz, because these sequential harmonics are going to have a difference which is equal to the fundamental frequency. And so you can see when you play guitar, graph B is what the actual pressure front would look like. So if you put a pressure sensor, like a microphone is a pressure sensor, in front of this guitar string, this is what if you have your computer plot it for you, this is what it would actually show. And so these two plots are actually, showing the same information, but in really different ways, right? Plot B is just what the air is doing in that situation, but plot A is kind of taking apart each component of the air's, oscillation and showing you those separately. And this is something that we sometimes take for granted. Like you can easily get a little music app or something that, like on your phone for free, that will tell you not only what this pressure front looks like, because that's just outputting whatever the microphone tells it is happening, but that'll also show you these frequency spectrum curves, where we get lines where each frequency that's present, with heights telling us their relative intensity. And the reason that we can do this is because you can kind of see it in this plot. So you can see how this thing has kind of like I drew that a little poorly, but it has kind of a sinusoidal nature overall. And then you can see how there's also some sort of sinusoid like this, which we could just draw up on the x-axis. And if we add those together, we're going to get something that looks more and more like this overall curve. So the takeaway here is that if we have some wave with some arbitrary scary shape, like, for example, the one on the bottom right here, that we can think of it in terms of a whole bunch of separate nice shapes, notably sine waves. So we can see on the left an example where we have this blue square wave. So that would be like, having, if you're just like slapping your hand on a desk or something, that would be a great example of a square wave sound. So it's actually composed of a lot of different frequencies. And we can see that this first red curve is what happens if we just have sort of the rough approximation of the square wave as a sine. But then we can add to that something like this. It's going to keep going, but you can see by adding this green curve to the red curve, we're kind of beefing it up in this region, and then we're kind of making it come down in this region, and that's what the second curve here is. This is this orange plot, and so as we add more and more frequencies that are all at different amplitudes together, we can create something that looks more and more similar to this square wave. So you can see by the time we're at the bottom picture, even though we've only used sine waves, we can make them look more flat on the top by using constructive and destructive interference to kind of smooth out those lumps where we would like to smooth them. And this process has a name, which is Fourier transform, or Fourier transforming. And this is one of the most important mathematical operations known to humans. I'm not exaggerating. There's a computer algorithm known as FFT, or fast Fourier transform, which is happening right now in all of your phones, watches, like any computer device does this. So not just for sound waves, but for analyzing its own internal waves that it's using to do calculations with. And so you don't need to know how to take Fourier transforms in this class. It's rather tricky to do mathematically. It involves a hard integral, but it's something that computers can do for us. And it's good to be aware that any wave you might experience, any periodic wave, can be described as a combination of a whole bunch of sine waves with different frequencies and different amplitudes. And it's just really hard to find out what those amplitudes should be. And that's where the Fourier transform comes in. And it's something your computer can do for you. But I want you to be aware of this terminology, just because now that you've heard it, you'll start to notice it in your life, that if you're reading scientific literature, they'll talk about Fourier transforms, and you'll start to see them pop up. Now you roughly know what they are. Okay. So I put a diagram of the human vocal tract here. So the lungs, of course, are down in this region, and they're feeding air up into the trachea. And then we have the voice box, which is this larynx region, which was originally just something that closed off the trachea to prevent food from entering it. But the muscles that are able to close the trachea can also vibrate. And so this is the spectrum of those vibrations. So your trachea is sort of right below your Adam's apple region. And so if you put a microphone and put it in contact with your skin there, as you speak, you'll get roughly this type of spectrum of sound waves. So you can see that there are a lot of different frequencies, and that there's more intensity as we get closer and closer to whatever that lowest possible fundamental frequency is for each individual person. So like for me, that's going to be something pretty low, but maybe if you have a higher pitched voice, your fundamental frequency is something a little bit higher. For example, maybe if you have a smaller vocal tract, or if you are speaking and stopping the air at a slightly different place. But anyways, and then we get a bunch of different tones, and this is all just happening from vibrations at the larynx. So not even thinking about the rest of the vocal tract. And then by moving, different parts of our mouth, our tongue, our lips, we can modulate this frequency spectrum. So this just monotonically decreasing spectrum, to get these little bumps, which in linguistics are called formants. And so those are the regions of the frequency space that actually contribute to what we consider the sound of a letter. So in the top picture, this is for an E sound. And so when I say E, this first formant is the fundamental frequency of that closed open system. And the second formant is coming from some higher order effect, because of the fact that this is all three-dimensional and there's a weird resonance in your vocal cavity. And you can see ah is an even more complex sound. So we're shifting that first formant forward, because like I said, with E, the length of that tube is shorter than with ah, the length is a little bit longer. So we're shifting that first format forward, and then we have the higher order ones that are coming from more complex effects in the vocal tract. And okay, so I think that's all that the book really had on the physics of speech. The most important thing here is just to understand that there's this process called Fourier transformation that exists, that allows us to produce these frequency spectrum plots and consider any sound, no matter how complex, as just a combination of sine waves that each have different amplitudes and different frequencies. Okay, any questions about 17.5? Good, good. So the next thing that we might ask is, and it's kind of weird that the book orders it this way, but I think they really want you to know about standing waves, and then they're like, okay, let's go and think about superposition a little bit more as well. But so we're kind of taking a step back, not looking at standing waves anymore, just thinking about this principle of superposition, so constructive and destructive interference. And so in 17.6, it's just thinking about constructive and destructive interference along a line. And what they want you to note is, so in this first set of examples, if we have two speakers that are playing the same sound, so this is common if you're at a concert or something, they'll have lots of speakers all playing the same concert sound. And they're on a line, so they're facing the same direction, linearly positioned, but they're separated by some distance, delta x. You might ask, at what separations, delta x, do we get some constructive interference, and at what separations do we get destructive interference? And so that's what these formulas are going to tell us. And basically the answer is that if the wavelength has traveled, if the wave has traveled an integer number of wavelengths by the time it gets to the second speaker, then the waves will line up, right? Because one wavelength just tells you that it's cycled back through and is at the same position as where it started. And since these speakers are playing the same sound, if that wave has come back to where it started by the time it gets to the speaker that's farther to the right, then the waves will line up and you'll get constructive interference. So that's what this equation is telling us. And you can see here m can be 0, but that's just a really boring situation where we have two speakers right next to each other. Of course, they're going to constructively interfere because the waves are exactly the same. And then for destructive interference, you just have to shift that over by 1/2. So we get these anytime that the wave comes to this earlier speaker and they're out of phase, so one is a trough and the other is a crest, they'll cancel out. And this is this is one way that we can get noise cancellation, where we have these two waves destructively interfering. And so if you stood anywhere over here, you would hear nothing if these were perfectly destructively interfering. But like I said, this isn't getting rid of the energy in the system because it's just a local effect. So as the waves travel outward, they still have their energy, even though they're not able to deposit it on something in this destructive region. Okay, so we can also talk about this type of interference in terms of phase difference. Let me see if I have an image for this. Okay, we'll look at the picture first and then come back to the equations. I should have ordered this better. So now the speakers, we can see on the left that they're at the same location, but we're playing the sound at a different phase. So you can imagine if we're playing some constant note, 100 hertz. But we are playing one such that the crests are at a different position in time than the other when they're emitted. Then that's some difference in phase, delta phi. And if that difference in phase is a multiple of 2 pi, then we get constructive interference. Whereas if it's a 1/2 multiple of 2 pi, we get destructive interference. So all that's saying is that if they line up, we get constructive, and if they are opposite, we get destructive. But we're just speaking in terms of phase, because you can imagine we can have these speakers be at the same location, but outputting sound at different phases. And so that's coming from this delta phi naught. And then we can add in that we maybe are also at different positions. And so putting all of this together, the example would be something like this option C, where you can see the wave here, it's has 0 displacement. Here it has maximal displacement. So the source of the sound is out of phase, and they're also separated by some distance. And so in this situation, if you want to figure out, is this constructive, is this destructive, what's going on, we can come back to this equation. And so we can say we have 2 pi times delta x over lambda plus this delta phi naught, and we want to know what that's equal to. So here they tell us delta phi naught is pi over 2, and they tell us that delta x is 1/4 of a wavelength. So plugging that in, this is another pi over 2. And so overall, these are separated by a phase of pi. And we can see here that a phase of pi is going to be one of these 1/2 multiples of 2 pi. I know that's confusing mathematically, but 1/2 of 2 pi is pi. So the sort of odd multiples of pi are the destructive case. So these are, to write these out, these would be pi, 3 pi, 5 pi. And so that's what's happening here. And we see, in fact, that when there's a peak here, there's a trough here. So these are destructive. So to use this 17.6 formalism, we want to write out what delta phi is, which is just, we want to use this equation. So this is delta phi. We want to use this equation where the delta x is how are these speakers positioned, how far away from each other in terms of the wavelength. And delta phi naught is how are the sources of the sounds out of phase at the point of the speakers. And by combining those two bits of information, we can get the total amount of phase difference between the two waves as they're propagating along the line, which tells us if it's constructive or destructive. So I know this is a lot of stuff to drop on you, but at the end of the day, this is just a mathematical way of saying, do the waves line up or do the waves, line up but opposite, so they cancel out. But it's just converting that into this language of angles makes for a tricky business. Okay, so I see lots of discussion, which is good. Do people have questions that are formed and you want to ask me, or is it just you kind of want to talk to each other, which is good. I mean, that's an important part of learning. Okay, so we can do an example here to give you some practice. And this might be all we have time for today, so we might have to finish up chapter 17 tomorrow. But we have 2 loudspeakers that emit the same frequency. So they both have a wavelength of 2 meters. Speaker 2 is 1 meter in front of speaker 1. Okay, so delta x is 1 meter, which is half of a wavelength. What, if anything, can be done to cause constructive interference between the 2 waves? Okay, so what they're asking then is we want to find what the total phase difference is between these 2 waves as they travel along a line. And remember, the phase difference is like basically what is this angle of separation between the peaks? This is delta phi, if we think of it in terms of an angle. And so this will be 2 pi delta x over lambda plus delta phi naught. And in order for this to be constructive interference, we want this to be a multiple of 2 pi, right? That's our condition back here. And so they already tell us that delta x is lambda over 2. So this whole first chunk, when we plug in, just becomes pi, right? The lambdas cancel, and we have a 2 that cancels a 1/2. So this just becomes pi. So we have pi plus delta phi naught equals 2 pi m. And the way that they set up this problem, they don't actually allow us to change delta phi naught, even though it looks like it in the picture, which is a little confusing. So actually all the options are just moving the speaker, so changing delta x. So you can see currently these are destructively interferent. If we don't move anything, the waves will be destructively interfering. And so what we can imagine is that if we just move this somehow another multiple of lambda over 2, the waves will have shifted completely again, and we'll have constructive interference, right? If we shift this over by lambda over 2, the peaks will line up and the troughs will line up, and we'll get constructive interference. And so, we can go through this process carefully and mathematically, but we could also just say that a shift of 1 meter is equivalent to lambda over 2 for delta x, which is equivalent to a phase change of pi. So shifting an extra 1 meter would certainly cause constructive interference, because we can plug this in. So shifting an extra 1 meter, well, if we move 1 meter backwards, the speakers are just next to each other, so that's going to be constructive. And if we shift a meter forward, now our delta x is 2 meters, which is 1 lambda. And so when we plug in our delta phi is 2 pi delta x over lambda, this is just 2 pi, which is a multiple of 2 pi, so that would be constructive. And then we could ask, well, what happens if we move 1/2 meter either way? So if we move 1/2 meter back, our delta x would be lambda over 4. And so that would cause a pi over 2 phase difference, which wouldn't be good. And the other way, cause a 3 pi over 2 phase difference, which also wouldn't be good. And so I think the options here, A and D, would both cause constructive interference. We could also say that if we made these two sources be completely out of phase when they leave the speaker, so if we made delta phi naught equal to pi, then that would also cause constructive interference, because then we would have a pi from them being separated by 1 meter and another pi from the sources just being flipped. Okay, so lots of mumbo jumbo here. Yes.
So why does that do? Is it because of you look at the pictures and they just show or black, right?
So we can just use our equations for each of these if we'd like, but we can also think about it in terms of the picture. So so for option A, we've moved speaker 1 forward, and speaker 2 is in front of speaker 1. So by moving speaker 1 forward, this is the case where both of the speakers are at the same position. So if the delta phi naught is 0 here, which as far as they tell us it is, then in this case, we would just have delta x 0, delta phi 0. So our total phase difference is just 0, which is a multiple of 2 pi. So that would be constructive interference. For option B, we move speaker 1 to the right 0.5 meter. So that would be a delta x of 1/2 meter, which is equal to lambda over 4. So we could plug that into our equation, and we would get a delta phi of pi over 2, which is bad because that's not constructive interference, which is what they're asking us to solve for. We could do option C, which again is a 0.5 meter, but now to the left. So this is going to cause our delta x to be 3/2 meters, which is 3/2, our wavelength is 2, so this is 3/4 lambda. So this would cause a phi of 3 pi over 2, which again is not going to cause constructive interference. Option D, 1 meter backwards. So now our delta x is 2. So our, which in terms of lambda would be just lambda. Our lambda is 2 meters. So our delta phi would be, 2 pi delta x over lambda, but the lambda just cancels. So this would be 2 pi. So again, that's good, that's constructive. And then the other options are like, did none of those work, or is it not possible? That sort of thing. So that's how we get A and D as the answers, yes.
You get lambda over 2, and you said that shifted.
So initially, they tell us that there's a 1 meter separation. So this is delta x. And they tell us the wavelength is 2 meters. So you could see a 1 meter separation would just be lambda over 2. Since lambda is 2 meters, 2 over 2 is 1. Yeah, it's tricky. I know I'm kind of going fast here. And saying maybe lots of letters and things, but you know, rewatch this if you need to, and you'll get some more practice as we go through the homework with thinking about these phase changes. Okay. Yes.
What about, condition by, so let's say it's been space, like 0.
Mhm.
Now, it's right now.
So are you saying that are you talking about delta phi or delta phi naught? So delta phi naught, I maybe didn't emphasize this enough. Delta phi naught is the difference in the phase as the wave leaves each of the speakers. Whereas delta phi includes that delta phi naught, but it also has the interference due to the fact that the speakers are at different locations along the line. So you can see how in this equation, this is just what it would be based on when the sound leaves the speaker. But this is based on their separation. And so the combination of those two tells us if the actual waves that get to our ear will be constructive or destructive. So for example, if you pop your AirPod in and turn on noise canceling mode, then that's going to record the outside sounds and play them back to you, but it will play them back to you slightly out of phase. And we said earlier that it plays them back to you out of phase by a factor of pi, because that would be destructive, but it's actually a little trickier than that, because there's also a separation delta x that it has to think about. So not only does it play it, it has some delta phi naught, but it wants the delta phi to be pi, right? It wants destructive to cancel out the sounds, to be noise canceling. And so it has to be from a combination of the delta x, the thickness of the AirPod, and the delta phi naught, the phase that the AirPod outputs. And that combination tells it sort of what to do in order to actually generate noise canceling. But the delta phi without the 0 is what actually determines if interference is going to be constructive or destructive. So you can see even with this simple type of analysis, we can already handle noise canceling headphones, because that's a very one-dimensional sort of effect. And so your AirPods do all of this calculation very, very fast. And actually the speed that they can do it is only limited by the fast Fourier transform function. So in order to do this phase shift, they have to do a Fourier transform to get the frequency spectrum and then be able to invert it and everything. So that can happen on the order of 1 millisecond, and it takes sound maybe 100 milliseconds to pass through an AirPod. So it's fast enough that it can cancel out the noise. Good question. Okay, I'm gonna leave it there for today. We're already a little bit over, but we'll finish up chapter 17 tomorrow and then move on to chapter 18, where we're going to talk about trickier wave phenomena.